Hello students, in this video we'll continue our competition preparation by doing a problem that involves the centroid of a triangle and a particular point inside a triangle. Let's be given a triangle, ABC, and then pick a point P interior to this triangle. And then form three centroids. Form the centroids as follows of PBC, then APC, and then ABP. Okay? Form those centroids and call them A tilde, B tilde, and C tilde respectively. Okay. Then we're going to prove the area of A tilde, B tilde, C tilde is 1/9 the area of A, B, C. Okay, great. Now, oftentimes when I have a problem that involves centroid, I like to use vectors for these problems. And so let's do that. And so let's recall, we've already seen in a previous video, so let's recall that if we write, if vector A, vector B, and vector C are the vectors representing these points in the plane, then the centroid has coordinates A plus B plus C over 3. Okay? So I can apply this result to each of those points, A tilde, B tilde, and C tilde. Hence, we can apply this to A tilde, B tilde, and C tilde. And what do we get if we do so? If we do this, we have that A tilde, the vector that corresponds to A tilde, is going to be what? It's going to be, well, A tilde is going to be a P plus B plus C over 3. B tilde as a vector, I'm suppressing the vector notation for this, is going to be what? Is going to be A plus P plus C over 3. And then B tilde, then C tilde, and finally C tilde is going to be A plus B plus P over 3, right? And so now what's the key feature over here? If I look at the vectors A to B, so what's B tilde minus A tilde? B tilde minus A tilde is going to be what? Is going to be A plus P plus C, vector, 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 minus P minus B minus C, all over 3. Great. And this is going to give me what? This is going to give me, let's see, the P's are going to cancel out, and the C's are going to cancel out. And that just gives me what? A third of what vector? A third of just A minus B. That's 1/3 of A minus B. Great. And then let's do C tilde minus A tilde. C tilde minus A tilde is going to be what? See, by the same reasoning, C tilde minus A tilde is going to be A plus B plus P minus P minus B minus C, all divided by 3. And that can give me what? The P's cancel, the B's cancel, and just gives A minus C, 1/3 A minus C. And then similarly, we get what? If I wanted to do B tilde, minus C tilde, for example, that would give me what? Well, that would give me 1/3 C minus b. Okay? So in other words, the side lengths, what does this tell me? This tells me the side lengths in this triangle, so the side lengths are a third of those in A, B, C. Great, there's our answer, right? And so in particular, what do we know? We know, for example, if I was to cross these two things over here, crossing those two vectors over here, and divide by 1/2 will gives me the magnitude, right? So in other words, remember that the area of a triangle, so if you have a vector over here, v, and a vector over here, w, then 1/2 the length of v cross w is the area of the triangle generated by v and w. Okay? And so what can we say? We can say, okay, if I cross these vectors over here, and of course, I'm going to get potentially a negative sign. It won't matter for this calculation over here, but 1/2 b minus a cross c minus a is the area of a tilde, b tilde, c tilde. But now each of these things I can pull out a 1/3, and this becomes what? A third and a third, so this becomes what? This becomes 1/9 of what? 1/9 of 1/2, and then b minus a or a minus b, doesn't matter, I can just flip the signs, cross c minus a, like that. And that's the what? That's 1/9, the area of A, B, C. And we just proved it. Great. Now, of course, the beauty of this method is I was able to use the formula, the actual vector formula for the centroid. That is a key feature of this proof. But the cool thing is that as an application of this, we can do exactly the same thing with a tetrahedron, right? I can give you a tetrahedron, right? And the volume of a tetrahedron is 1/6 the triple scalar product, which means the only difference in this problem, the three-dimensional problem for the tetrahedron, is that the centroid of a tetrahedron is A plus B plus C plus D over 4. Right? And so now I have a fourth of what? In the triple scalar product, so I have a fourth, and a fourth. So I get 1/64, the volume of the original one, if I was to take this into higher dimensions, right? And so this idea with vectors generalizes to these higher dimensional configurations, right? As long as you can make sense of what it means to be a centroid, right? And the centroid is always the what? Is always the average, right, of all of the vector components of the vertices, and that comes in real handy when we're doing problems with centroids. So always, always, always think, if there's a problem that involves the centroid, try to lean on the vector formulation of this, because the vector formulation, this is an average of the vectoring, and that averaging is a very powerful tool in competition problems. Thank you very much.